Annenberg Media.
Why is it windy sometimes? Why do puddles disappear? Why do I see clouds moving two different directions at the same time?
We all know something about the weather because we experience it firsthand every day. It dictates the kind of houses we live in, what types of clothes we wear, and often the types of activities and sports we engage in. Welcome to the final session of Shedding Light on Science, Wind and Weather. I'm Christine Jones from the Harvard-Smithsonian Center for Astrophysics.
And I'm Anita Greenwood from the University of Massachusetts Lowell. Today we will explore how the absorption of light energy results in the weather we experience on Earth. In particular, we shall investigate how the atmosphere raises the Earth's average temperature, how it evens out temperature differences between day and night, how the air and oceans redistribute energy from the Earth's equator towards the poles, how differences in temperature or air pressure cause winds, and how clouds form.
The sun continuously emits photons of light energy, and the tilt of the Earth's axis with respect to the plane of its orbit around the sun determines the amount of light energy hitting parts of the Earth at different times of the year. This causes seasonal changes. Even with seasonal changes, there is more sunlight in the equatorial region than on the poles. As we'll see, the greater amount of light energy that the Earth receives from the sun near the equator is an important factor in our weather.
Temperature in Boston this evening, 43 degrees after a daytime high of 50. Worcester now 37, 39 degrees in Providence, 40 degrees in Hyannis, and 41 in Manchester. A cool night with... Meteorology as a science attempts to give reason to the way that air moves and moisture is transported around the globe. We know that the driving engine behind that is the sun and the light that comes from the sun, and that eventually puts weather patterns and air masses into motion, and that equates to sensible weather on a daily basis. The weather is the day-to-day changes that we experience in our lives from atmospheric variation. Climate, however, is the long-term patterns. It's sort of the average or the norm. Climatology is a science that studies long-term patterns of the atmosphere. So when you talk about the climatology of Boston, you talk about 30 years of weather data, and you average that weather data over that 30-year period, and on today's date, the average temperature would be 49 degrees for a high. That's the average. That's sort of the climate of our region. We're in a particular latitude and longitude, so given that, we have a sun angle that varies to a certain degree during the course of a year, and that translates into the climate that we know, our average weather here locally.
We'll be joined by Mish Michaels throughout this workshop. Weather occurs in the part of our atmosphere known as the troposphere, which extends to a height of about 10 kilometers from the Earth's surface. Above this layer is the stratosphere, extending to about 50 kilometers. Most of the ozone is found in the stratosphere. Ozone is a gas that absorbs ultraviolet light, preventing most of these high-energy photons from reaching the Earth's surface. If the Earth were the size of this globe, the atmosphere would be as thin as this cardboard.
The presence of the atmosphere profoundly influences temperatures here on Earth. To understand this, we can look at conditions on the Moon as an example of what the Earth might be like if it had no atmosphere. Temperatures on the Moon are extreme. Without an atmosphere to protect it, the sunlit side of the Moon is extremely hot on the surface, about 127 degrees Celsius. While the temperature on the side away from the Sun, the dark side, plummets to about minus 173 degrees Celsius, really cold.
On Earth, our atmosphere allows mostly the visible and infrared photons from the Sun to reach the Earth's surface. While our atmosphere makes the temperature less extreme, its presence also changes the Earth's average temperature. The Earth's average temperature is about 40 degrees Celsius higher than it would be if the Earth had no atmosphere. Our atmosphere acts like a blanket, helping to maintain the heat. Some of the infrared radiation given off by the land is absorbed by the clouds and carbon dioxide in the atmosphere. It is then radiated so that some of the energy is returned to the land. We call this the greenhouse effect. This is basically the same reason that a greenhouse or a closed car on a sunny day feels warmer inside than outside. Visible light comes in through the car windows and heats the car's interior. The hot surfaces inside the car radiate infrared photons. Since the infrared photons do not readily pass through glass, the energy is trapped inside the car. So the air inside the car gets hotter than the air outside.
Let's begin our exploration of weather by looking at what happens to light energy when it reaches the Earth's surface. We visited Lolita Darby's 5th grade class in Portland, Oregon, as they conducted an experiment to find out what happens when light energy falls on water, sand, clay, and loam.
Which of these is going to heat up the most? The sand, the loam, the clay, or the water? Which is going to heat up the most?
I think the sand's gonna heat up the most.
Why do you think that?
Because, like, if you was on a beach, the sun reflects onto the sand.
Which is going to heat up the least?
I think the water, because if it's cold water and then the heat will go against it and then it will like make it warm. It'll take it a while to warm up.
I think clay will heat up the least.
I think the loam will heat up the least because it isn't stuffed in like most kinds, so it has like air holes, so it'd take longer to heat up.
Is it past your line? Shake it around.
Okay, you done? Okay.
Perfect. Is that it? Perfect. Good. Okay, you got this? Okay. Okay, fine. You're good. Is there anyone else that needs to come and get Loman and
Man,
almost. Remember, you need to sit in the seat. Good.
I got mine in there. I went from 20 to 18.
It looks like it's between 22 and 21.
27.
Darby, I need one.
What is the water?
That's what I'm turned around.
How high is sand?
Ah. Okay. I saw this.
Okay, what's below?
Okay, then go ahead, Andy.
I got
Below means the sand.
Okay, let's see.
Oh my God,
The sand is about 20, about 28.
27. 28.
Sand is 28. The loam is
The water
31. It went up about one degree. Oh, this went down.
Okay, the sand went up 3. The loam, what is it called again? Loam went up 4, and then the water went up 1.
The children discover that sand, clay, and loam show a faster rise in temperature than water.
27. That's 30. No, and it's right under 30. So it's 29.
But if the children had turned off their lights and let the sand, loam, clay, and water start to cool down, they would have found that just as sand gets hotter quicker than water, it also gets cooler quicker. It takes about 5 times the amount of light energy to heat water than it takes to heat sand by the same amount. The water takes a longer time to radiate or lose this energy. This has important implications for weather.
The ocean water temperature is different than the land oftentimes because of the heat capacity. The way that light transmits the heat, that heat is absorbed over a longer period of time in the ocean, so the ocean heats up more slowly and cools down more slowly, whereas the land can heat up quickly and then cool down very quickly. And so if you have a body of water to the west of you and weather is traveling all the ways from west to east, the air mass is going to moderate over that body of water to some degree, and that air mass is going to pick up a lot of moisture. And so, like London, it rains a lot. Temperature doesn't vary all that much. They don't usually get all that cold. They don't usually get all that warm because the ocean water to their west really doesn't get all that warm in the summertime. It doesn't get all that cool in the wintertime. Whereas a city on the very same latitude is governed by, say, the topography. If it's landlocked and there's no area of water to the west of it, the air mass doesn't moderate. The air mass can remain very cold or very warm, and that translates into a greater variability, even though it's the same latitude, and the heat budget based on the sun angle is the same all year long. The weather can still be very different.
We have now seen that light energy heats the land and water. So how does this influence the temperature of our atmosphere? The land or water heats the air above it, and warm air rises. Let's return to Lolita Darby's 5th grade class, where the children are measuring the air temperature in their school gymnasium.
Now, let it go up as high as it'll go, and we want to watch it for 3 minutes. Uh-oh. Okay, would everyone please get their data sheets?
The children record the temperature of the air in their school gym at 5, 10, 15, 20, and 25 feet.
We can't hold it.
Like right here, so we were
35, 35,
35, 40,
40,
45, 50.
50.
So that's like 50. I was about close. And we, see.
By reading the thermometers quickly, they're able to get an estimate of the temperature at each height.
About 28. About 28. What if we were to discover 30 feet? If 25's here, 30.
25, 30, 35, 40.
They find that in their gymnasium, the higher the balloons, the warmer the air.
29, 20 for 40 feet, we got 29 feet. For 35 feet, we got 29 feet.
What were we looking at, Michael? What were we looking at?
Oh,
Michael Cross? What were we looking at?
well, we were looking
Or
at,
measuring.
we were measuring for Celsius to see at different levels to see how high, if the temperature, if the temperature in Celsius will rise or if it will drop down low.
Look at the comparisons that we made here. Look at the pattern. What pattern do you see? What do you have at 0 feet? How many Celsius? Degrees Celsius?
26,
What do you have at 20 feet?
30,
What do you have at 20 feet, Jennifer?
28.
28 degrees Celsius. Okay, what pattern are you beginning to see? Okay, go ahead, Duran.
It's a big change from 0 feet to 20 feet because it was 23 at 0 feet and 28 at 20 feet, and it's 5 Celsius. 5 degrees different.
when the height gets higher, then the temperature get higher.
Very
Once
good.
we go like to fifth, like if we went to like 5, the temperature went higher on 27. Then if we went on 10, the temperature went higher on 28.
But why does warm air rise? Let's look at the behavior of an air-filled Mylar balloon. We place a Mylar balloon filled with air in a freezer for 5 minutes. When we take the balloon from the freezer, it is partially collapsed. The air inside is colder and the whole balloon is smaller. The air is taking up less space or volume. We leave the balloon in the room. The air gets warmer and the balloon gets larger as the air takes up more space, more volume. When air gets warmer, the particles of which it's made start to move more rapidly and move further apart. This is why the air takes up more space and the balloon inflates. We say that the air has expanded. The warm, expanded air is now less dense than the cooler air surrounding it, and it rises.
During the day, land heats up more efficiently than water. The air above it is also heated more than the air above water. The warm air above the land rises and is replaced by cool air from over the water. This circulation of warm and cool air is known as a convection current. Let's look at a convection current more closely.
Because land heats up more efficiently than water, on a summer afternoon, the land is warmer than the water. The air over the land is heated and rises. Cooler air from the water replaces the air that has risen. So we feel a breeze coming from the water to the land. Because water retains heat longer than land, in the night and early morning, the land is cooler than the water. The air is warmed over the water and rises. Cooler air from the land flows toward the water. A breeze of cool air blows from the land to the water. Breezes are caused by moving air. Moving air is what we call wind. Convection currents also occur on a larger scale because vast regions of our Earth are unequally heated. Warm air from the equatorial region will expand and rise and flow over the cooler air, with the warm air spreading outwards toward the poles. As the warm air from the surface rises up and away, it is replaced by cooler air flowing at ground level from the poles. If the Earth didn't rotate on its axis, the sun's uneven heating would cause a general circulation in the atmosphere, with warm air rising in the equatorial regions and sinking at the poles.
We can demonstrate convection using this container of water to represent the atmosphere. Air and water behave the same in many respects when it comes to convection. We will support each side of the container with a small container of ice, and under the center of the container, put a cup filled with hot water. Heat from the hot water represents heat radiated from the land and water near the equator. The ice represents the polar regions. Finally, we add a puddle of food coloring over the cup of hot water. As the water in the container is heated, it rises. As the warm water reaches the surface of the water, it spreads out, cools, and eventually sinks back down, is warmed again, and rises once more. We see two convection currents or cells, one on each side, as the water circulates. These are created by temperature differences produced in the water by the cup of hot water and the containers of ice. Now let's look at how convection currents might occur with a globe. Here we see only the northern hemisphere, and again we're using water to represent the atmosphere. We see the warmed water with the food color from the equatorial region rising and flowing north. As it reaches colder northern latitudes, it sinks toward the surface of the Earth. As it sinks, it begins flowing back toward the equator, where it will begin the cycle again. But if it happened just like this, we would have the effects of rising warm air near the equator replaced by cooler air flowing toward the equator from the poles. But our Earth rotates on its axis, making the situation more complicated. Because the circumference of the Earth is greatest at the equator than it is at any higher latitudes, the speed of rotation is highest at the equator. The Earth's atmosphere travels with it, so the air over the equator is moving faster than the air and the ground at higher latitudes. As we move from the equator toward the poles, the distance around the Earth gets shorter, and therefore the speed due to the Earth's turning is slower. For example, at our latitude of 42 degrees here in Boston, our rotational speed is about 20% less than the speed at the equator, and at the poles, there's no rotational speed. At the equator, the atmosphere is moving eastward at about 1,700 kilometers per hour, while at latitudes of 42 degrees, it's traveling eastward at only about 1,300 kilometers an hour. If the atmosphere did not travel with the Earth, at the equator, clouds would appear to move across the sky at about 1,700 kilometers an hour. Therefore, as hot air rises over the equator and flows toward the poles, it's traveling faster in the direction of rotation than the Earth below it. The effect is that air is deflected to the right of its path in the northern hemisphere and to the left in the southern hemisphere. In this demonstration, we are using a pan of water in which we mix an opalescent pigment. A miniature pump is placed at the edge of the pan, and the pan is set on a turntable. If the pan is not rotating and we turn on the pump, we can clearly see that the water current flows directly toward the pan's center. However, if we rotate the pan, we can see that the current curls toward the direction of rotation and does not flow directly toward the center. This deflection is called the Coriolis effect, after Gustav Gaspard Coriolis, who first explained it mathematically in 1835. Because of the Earth's relatively rapid rotation, the velocity of the warmer air from the equator would be much greater than the velocity of the cool air moving from the poles toward the equator. Thus, the actual atmospheric circulation is not a single pattern from the equator to the poles, but rather occurs in 3 regions of latitude in each hemisphere.
Air that rises in the tropics and travels toward the poles tends to sink to the surface of the Earth at latitudes of about 30 degrees, and then flows back to the equator. Some warm air continues to move toward the poles. At about 60 degrees of latitude, this air meets the cold polar air. The difference in temperature causes the warmer air to rise, while some flows back toward the equator, sinking to the surface at latitudes of about 30 degrees. Some air continues to move toward the poles, descending over the polar region and flowing back toward the equator. Our atmosphere works to smooth out temperature differences, primarily by carrying warm air from hotter regions near the equator toward the poles, and bringing cold air from the poles toward the equator.
Although you may not think about it, air has weight. The weight of the air pushes with a force that we call atmospheric pressure.
Our first stop is the H. H indicates an area of high pressure, an area where air tends to be sinking, so there is more weight over top this particular area than elsewhere. An area of high pressure usually produces clear skies, and in this case, it's associated with an air mass that includes cold weather. Just to the east of that is a big L. This is an area of low pressure, and this indicates that relative to the area of high pressure, air is generally lifting and moving away from planet Earth, so there is less pressure at the ground level. When you have lift, therefore you have cloud development. Now, also with an area of low pressure, winds tend to move towards the center of that air pressure or that area of low pressure in order to fill in that void. And as the air moves towards that area of low pressure, you bring together areas of different air qualities or different air masses. So this area of low pressure is bringing in towards the center of it different air masses. One air mass that includes cold and dry conditions from the northern plains, and another air mass which includes moist and warm conditions which are pluming up from the tropics. The leading edge of these two separate types of air masses are denoted by frontal boundaries. The leading edge of that warm and tropical air mass is called a warm front. That is shown by this little line, this red little line, with a few little lumps right along it. That is a warm frontal boundary, the leading edge of that warmer tropical air. This cold front is the leading edge of that colder and drier air. Here in this case, it's pushing that moisture up and lifting it along a very narrow line where showers and thunderstorms would likely form. In the case of a warm front, that warm air only slowly rides up and over the cooler weather, and that usually produces a broad area of very light precipitation, or sometimes in some cases moderate precipitation.
Light energy is responsible for heating the Earth, which in turn heats the air above it. This creates air masses of different temperature. Winds move these air masses around the globe. A warm front is where warm air is displacing cold air. A cold front is where an area of cold air is displacing an area of warm air.
So let's talk in greater detail about what air masses actually are. Air masses, the definition of them, is a broad area of air that has similar characteristics on a horizontal scale, that being similar temperatures and similar content of moisture on the horizontal. Our first stop during the long winter months when there is very little sunshine and very long nights, very cold air masses can evolve in the northern reaches of Canada up towards the Arctic Circle. Because this air mass becomes stagnant and kind of sits here for a while, it takes on the characteristics of those cold and dry nights. With very little moisture and very chilly air, this is termed a continental polar air mass. Oftentimes in winter, it slides down the eastern Rockies and eventually swings into the eastern United States and makes for a big cool down. But again, usually it is associated with dry conditions because there's not a lot of moisture for it to gather in that particular region. In the meantime, maritime polar air that comes in during the winter months along the Pacific Northwest actually originates as continental polar air over in Asia. It makes a long trek across the North Pacific and thereby it picks up lots of moisture, so it translates instead into a maritime polar air mass. And this maritime polar air mass is usually associated with cool, moist, kind of damp conditions, and that's what creates the constant showers and drizzle and low clouds and fog that seem to plague the Pacific Northwest. When you add a little elevation to that, the air cools and instead falls in the form of snow in the Olympic Cascades and some of the higher elevations along the west coast. Now let's take a look at some of the warmer air masses. Here we have a maritime tropical air mass which originates over the Gulf of Mexico and the Caribbean. During the summer months, this is where we can see this expand north and eastward and eventually bring a heat wave to the eastern United States. As you can see, it's close to the equator. There is plenty of sunshine, and that means lots of warmth. But because this air mass originates over water, it is considered maritime tropical. So very warm and tending to be quite moist. This is one of the regions where we'll see tropical storm development during the summer months. Another and not so common air mass is continental tropical air, and this swarms over the drier, more arid areas of the southwestern United States and northern Mexico. The air here is very warm and exceptionally dry. In fact, in order to build a cloud up, you have to sometimes lift it all the way up to 10,000 feet. And so there's very little moisture to work with, and therefore a continental tropical air mass is very warm, very dry, and quite comfortable with really no precipitation falling. And it really doesn't have much of an impact on the weather elsewhere, as it usually moderates or modifies and changes, taking on the characteristics of other surfaces as it moves about towards the central United States or into the Gulf of Mexico.
Where fronts meet, we see distinct cloud formations. If a warm air mass moves into a region of cold air, the warm air will rise over the cold. Warm air can hold more water than cold air. That's why we usually have more moisture in the air in the summer. So as warm air rises over the cold air, the warm air will expand and cool to a point that it cannot hold all of its water vapor. Some water vapor will condense into droplets and a cloud will form. When the droplets of water in the cloud grow too large to be kept aloft by rising currents of air, it rains, or if it's cold, it snows. Observing clouds is one way we can make predictions about weather changes. It was Luke Howard who developed a classification scheme for naming clouds.
In 1783, the London sky was laden with dust and ash from volcanic eruptions in Iceland and Japan. 12-year-old Luke witnessed a fiery meteor that flashed across the Western European sky. young Luke became interested in the sky and for 30 years was a devoted amateur meteorologist. In fact, he is credited with developing the first scientific system for naming the clouds based on their shape, thickness, and height. Cumulus is Latin for heap. Stratus is Latin for layer. Nimbus is Latin for rain. Cirrus is Latin for curl. These categories and names are still used by meteorologists all over the world.
We've probably all noticed different types of clouds, but what is the connection between light energy and clouds? Well, clouds reflect some sunlight back into space. They also absorb sunlight. Only about half the sunlight that shines on the Earth reaches its surface. And nearly half of the sunlight that reaches the Earth's surface is used to evaporate water from oceans, rivers, and ponds.
Suppose the sky were always covered with a layer of clouds. How might this change weather conditions on the Earth? Often, at lower grades, we do not talk about the molecular nature of materials. But it's difficult to understand ideas such as evaporation and condensation without some understanding of matter. Children can begin to develop an understanding of the behavior of the particles or molecules. Let's listen to some interviews with Jean Huff's third graders after their unit on solids, liquids, and gases.
Molecules they want to go so far apart that because they don't want to be around each other because they don't like to be crowded, like scrunched up like solids, and they don't want to be just a little bit apart like liquids. They want to be like running a race, and they want to be in first place, and they want the other people to be, the other gas molecules to be far behind.
When my mom brews up the kettle into hot water, when steam comes out of the spout, it doesn't stay in one clump. You can see it coming out, but then it spreads around in the air and you can't see it then.
Do you think the molecules are different in the solid and the liquid when they're in ice and in water?
They're different, yes.
They're different. How are they different?
Well, this couldn't be a liquid because it's all crunched up like a solid. Yeah. And this couldn't be a solid because it's all like a liquid. Except if you froze this, then it would be this.
So what happens to make it go from one to the other?
Well,
How do the molecules manage to change over?
Maybe, I don't know.
Is there anything between the arrows?
In between, well...
In between the molecules, like in here or in here?
Yeah, there is.
Yeah? What is there?
There's more molecules. I'll make these a little smaller. Maybe that one's hard to see. And then there's some more. Now, for gases, there could be some and could not because they want to get get away, you know.
Yeah.
So, probably not, but there could be.
Probably not, but there could be something in there.
Yeah.
If there
could be another group down here going up there, so.
Another group of what?
Gases somewhere down there, like from downstairs. This is like the second floor in a house. Now there's nothing in the middle in the second floor, but the first it goes up the stairs into the middle.
I see. Yeah. What makes the molecules move?
That I don't know yet.
You don't know that yet?
Yeah.
Okay, so you still have something to learn.
Yeah, we still have more things.
Yeah, well, that's okay, because you're in
third
grade, so, you know.
It's something that you put on your skin to make yourself smell better.
That's it, absolutely, you got it.
It smells funny.
Do you have to touch your nose in order to smell it?
No.
No.
Here is the drop of cologne. And then here are the tiny little bits going up, and here is
You want to draw your nose? Okay.
And it smells the tiny bit.
What do you think those bits are that are going up to your nose?
Molecules, probably.
Where'd the molecules come from?
The cologne.
So how did they get? The cologne is what in here?
A liquid.
Uh-huh.
It's starting to evaporate.
And so when the liquid evaporates, what happens?
It goes up into the air.
What goes up into the air?
The cologne. It's just tiny bits that you, tiny microscopic bits that come out of the cologne, and then there's millions of them in just a tiny empty dot here, so it would probably still stay there for a while. If you had a liquid and wanted to turn it into an ice cube.
Supposing I wanted to turn some of this water into an ice cube.
You could freeze it.
Oh, I could freeze it. And what does freezing do?
It brings all the molecules tight together. Then they get colder and they get closer together and closer together until they're touching each other.
I see. Are they still moving?
They can move just a tiny weensy bit.
The children explain that molecules move differently in solids, liquids, and gases, but we're not sure of the cause. The children were missing the idea that energy is needed to change materials from solid to liquid to gas. For children to be able to understand how clouds form, they must understand that water can exist in different forms, and that one form can change into another and back to its original form. In this demonstration, we have placed hot water in a glass jar and a pan of ice over the top of the jar. Some water evaporates and becomes part of the air in the jar. The hot water warms the air that rises. The air meets the ice pan and cools. Water vapor in the air condenses, and we see droplets on the pan. This demonstration provides two of the conditions needed to make clouds: water vapor and cooling air. But no cloud appeared in our jar because the third condition is missing. A cloud must have particles suspended in the air itself for water vapor to condense upon. We repeat the demonstration, but this time we place a match in the jar. As the smoke particles rise into the jar, we see a cloud begin to form. The smoke particles act as condensation nuclei. They are small particles such as sand, salt, dust, or pollen in the air. Condensation nuclei act as a surface to which condensing water vapor can stick.
For clouds to form, there must be water vapor in the air, but the amount of water vapor varies.
We have seen that the energy of light heats the Earth's surface, both land and water. The heated Earth warms the air above it. Warm air rises. The rising warm air is replaced by cooler air, setting up a convection current. Light energy also causes water to evaporate from lakes, oceans, and ponds. The water vapor becomes part of the rising air. When warm air rises, the water vapor within it condenses at high altitudes, forming clouds. All clouds contain minute water droplets, but they do not all produce rain or snow. Cloud water droplets are far too small to reach the ground without evaporating, so a mechanism must exist for creating larger droplets. Water droplets in clouds must coalesce in order to form precipitation and return water to the Earth, completing what we commonly call the water cycle, the continuous exchange of water between the atmosphere and the Earth's surface.
Throughout this series, we have shown the importance of light energy for life on our planet. We hope that for you, we have shed some light on science.
We hope this series has piqued your curiosity to delve deeper into some of the concepts that we explored. We encourage you to continue to use the website and Channel Talk. Please post your ideas, comments, and your strategies for integrating light topics into your teaching.
Thank you for being with us. Our web address is www.learner.org/channel/workshops/shedding-light. And if you don't have access to the web, you can share your thoughts with us by email, fax, or mail. Our email address is channel@learner.org. Our fax number is 617-496-7670. Our mail address is the Annenberg CPB Channel, Smithsonian Astrophysical Observatory, 60 Garden Street, MS-82, Cambridge, Massachusetts, 02138.
Annenberg Media. For information about this and other Annenberg Media programs, call 1-800-LEARNER and visit us at www.learner.org.